Can anything go faster than light? Have you ever wondered if there's some cosmic speed limit, some universal rule that nothing, absolutely nothing can cross? It's a question that makes you scratch your head. A speed limit in the universe? Not on a highway, but across space and time itself. Today, we're going to dive into this mystery, and I promise it won't just be theory. By the end of this video, you'll understand it physically, you'll feel it in your bones, and you'll see why the universe has built-in rules far stranger and more beautiful than science fiction could ever imagine. Let's start with something ordinary, something you do every day without even thinking about it. Imagine you're sitting on a train, nice and smooth, curtains drawn, and you can't see outside. Now, here's a simple question. Are you moving? You might say, well, let me look out the window. But the curtains are drawn, so that won't help. Instead, you take a ball out of your pocket and toss it straight up. It comes straight back down into your hand. Does that tell you if you're moving? Nope. Whether the train is sitting still at the station or gliding along at 60 miles per hour, the ball behaves exactly the same way. Up and down, up and down. No difference. This puzzled some of the greatest minds in history. Galileo, Newton, they realized something profound. There's no experiment you can do inside that train to measure your absolute speed. You can only measure motion relative to something else, like the tracks, another train, or the trees outside. Absolute speed, it doesn't exist. Motion is relative. Now let's take a leap from trains to something truly cosmic. Enter James Clerk Maxwell, a brilliant mind who wrote down the equations of electricity and magnetism. Hidden in those equations was a number that would change physics forever. The speed of light, about 186,000 miles per second. But here's the kicker. The equations didn't say 186,000 miles per second relative to the Earth, or relative to the Sun, or relative to anything else. They just said 186,000 miles per second, period. Now, if you've ever thrown a baseball from a moving car, you know the rule. Speeds add. Go 60 miles per hour in a car, and throw the ball 50 miles per hour forward. The person on the sidewalk sees it moving, 110 miles per hour. Common sense. That's what Galileo would tell you. So imagine this. You're on a train moving at half the speed of light, and you shine a flashlight forward. Classical intuition says the light should travel at 1.5 times the speed of light for someone standing on the platform. Half plus 1 equals 1.5, right? Wrong. Dead wrong. Every precise experiment shows the light still moves at exactly 186,000 miles per second no matter what. Towards you, away from you, sideways, spinning in circles, it doesn't matter. The speed of light is constant for every observer, everywhere, all the time. And that, my friends, is where things get really interesting. Classical ideas of space and time simply can't explain it. Something had to give. Enter Einstein, who said, if this is what nature is telling us, let's take it seriously. Let's rethink everything we thought we knew about space and time. All right, now we come to Einstein's big insight, the one that turned everything on its head. The principle is simple, but revolutionary. The speed of light is the same for everyone, no matter how fast you're moving. At first, it sounds impossible. How can two people moving relative to each other both measure the same speed for the same beam of light? But experiments confirm it every single time. And if the speed of light is constant, then something else has to change to keep the equations balanced. That something else is time. Let's do a little thought experiment. Imagine a very simple clock, a light clock. 2 mirrors, 1 pulse of light bouncing up and down. Every time the light hits the bottom mirror, that's a tick. Now put this clock on a train moving at a tremendous speed, say, half the speed of light. You're standing on the platform watching. From your perspective, the light doesn't go straight up and down anymore. It traces a diagonal zigzag path as the train moves. The light still travels at the same speed, but the path is longer. Longer path, same speed. What does that mean? It takes more time. From your point of view, the moving clock is running slow. This isn't an illusion. Time itself is flexible. When you move relative to someone else, your time literally slows down from their perspective. And here's the kicker. From your point of view, you're standing still and the other person is moving. So each of you sees the other's clock running slow, and you're both right. Space and time are not absolute. They're intertwined, dynamic, and flexible, stretching and squeezing depending on motion. Welcome to time dilation, the universe's way of keeping the speed of light constant and showing us that our everyday notions of time are only approximations for slow speeds. Let's dive deeper with a thought experiment. This one really makes relativity tangible. Imagine the simplest clock you can think of. Just two mirrors and a pulse of light bouncing between them. Every time the light hits the bottom mirror, that's a tick up, down, tick. Simple, right? Now, put this clock on a train moving very fast, say, half the speed of light, and you're standing on the platform watching. From your eyes, the light isn't moving straight up and down anymore. Instead, it zigzags diagonally as the train moves along the tracks. The light still travels at the same speed always, but its path is longer. A longer path at the same speed takes more time. From your perspective, the moving clock ticks slower. Time itself stretches when things move fast. And this isn't just imagination. We've tested it. Atomic clocks on airplanes, particles in accelerators, they all confirm the same thing. Time dilation is real. The universe is telling us, gently but firmly, time isn't absolute. It bends, it flexes, depending on how you move. Let's make sense of this time dilation. Remember the basic formula. Speed equals distance divided by time. If the speed of light is fixed for everyone, but the distance it travels changes depending on how you're moving, then time itself has to adjust to keep the equation balanced. That means you and I, moving relative to each other, experience time differently. Your seconds might be longer or shorter compared to mine, and mine compared to yours. Time isn't universal. There is no cosmic stopwatch ticking the same for everyone. No absolute now. Each of us carries our own personal clock, shaped by how we move through the universe. It's mind-bending, but this is what reality does. Time bends, stretches, and flexes. It's not an illusion. It's the universe whispering, "This is how I really work." Now, let's clear up a big misconception. You've probably heard, nothing can go faster than light. Sounds simple, right? But the real idea is subtler and more fascinating. If you have mass, anything from a baseball to a spaceship, you can never accelerate to the speed of light. The closer you get, the harder it becomes. Why? Because as your speed increases, your resistance to being pushed, what physicists call relativistic mass, grows. It's like trying to push a car up a hill that gets steeper the faster you go. Some people ask, what about tachyons? Hypothetical particles that always move faster than light. Sure, math allows them to exist, but they'd have bizarre properties, imaginary mass, backwards in time effects, and violations of cause and effect. Physicists mostly think they don't exist, because if they did, our universe would get, well, nonsensical. So, here's the takeaway. Light isn't just a speed limit on a highway. It's a fundamental boundary built into the structure of reality. Massy objects can get close but never cross it. And that's exactly what makes the universe work the way it does. All right, now let's talk about something that changed physics forever. Einstein's famous equation, E equals mc squared. What does it mean? Energy and mass are two sides of the same coin. When you speed up an object, you're giving it energy. Kinetic energy, the energy of motion. But if energy and mass are equivalent, that means the object's mass increases as it gets faster. Think of it like this. Imagine running in a race where every step you take actually makes the finish line move farther away. The faster you try to go, the more massive or resistant you become. Push harder, you get even more mass. It's an endless cycle. That's why reaching the speed of light for anything with mass would require infinite energy. And, last I checked, nobody has infinite energy lying around. So, the light speed limit isn't arbitrary. It's baked into the relationship between energy, mass, and motion. Massless things, like photons, the particles of light, aren't bound by this. They always travel at c, the speed of light, because they have no mass to hold them back. That's why light is special. That's why it's the cosmic speed limit. Let's dig a little deeper into mass and energy. Einstein told us that mass and energy are equivalent. That's E equals mc squared. It's not just a neat formula. It has real consequences. When you add energy to an object to make it go faster, something interesting happens. Its mass effectively increases. It's like the object resists your push more and more the faster it goes. This is why we can't simply accelerate a spaceship to the speed of light, no matter how much fuel we throw at it. Now, physicists call this relativistic momentum. Unlike Newton's classical momentum, which is just mass times velocity, relativistic momentum grows faster than you expect as speed increases. At everyday speeds, it looks normal, but as you approach light speed, the mass keeps increasing toward infinity, and the acceleration slows down to almost zero. So mass isn't just a measure of matter, it's a measure of resistance to acceleration, and energy is what fuels motion. Mix them together, and you see why the universe enforces a speed limit. Light just happens to be the fastest thing because it has no mass to slow it down. Now let's take a step back and look at the universe from a space-time perspective. Here's a strange but beautiful idea. Everything always moves through space-time at the speed of light. If you're sitting still in space, all your motion is through time. That's why your clock ticks normally. But the moment you start moving through space, some of that motion through space-time gets redirected into space, which means your motion through time slows down. Time ticks slower for you compared to someone at rest. Take it to the extreme. Photons, the particles of light, move entirely through space. They travel at light speed, which leaves no motion left through time. For them, time doesn't pass at all. That's why, in a sense, light is timeless. Its journey from a distant star to your eyes happens in an instant, no matter how many years it takes us to see it. Let's see what happens when we compare the massless and the massive. Photons, the little packets of light, are massless. They always move at light speed, no exceptions. And because of that, they don't experience time at all from a photon's point of view. The journey from a distant star to your eye is instantaneous. Now look at us, massive objects like people, planets, spaceships. No matter how hard we try, we can never reach light speed. There's always time ticking along for us, always a before and after. The speed of light isn't just a fast number. It's a cosmic boundary, a dividing line between things that experience time and things that don't, between the world of the massive and the world of the massless. Imagine this. You invent a magic instant phone. You press a button, and a message reaches a friend light years away instantly. Sounds amazing, right? But here's the kicker. If information could travel faster than light, the order of events could get all scrambled. Your friend could receive the message before you even sent it. Cause and effect, flipped upside down. Physicists call this a violation of causality. And that's no small problem. Our universe depends on cause happening before effect. So the speed of light isn't just a speed limit. It's a cosmic rule that keeps the universe from falling into chaos. Now let's peek into the weird world of quantum mechanics. Particles can be entangled like two cosmic twins that mirror each other instantly, no matter how far apart they are. Whoa! Instant action at a distance. Does this mean faster than light communication? Not quite. Here's the subtlety. Entanglement correlates outcomes, but doesn't send usable information faster than light. No messages, no causality violations. The universe still respects the cosmic speed limit. Even in the strangest quantum corners, Einstein's rule holds light speed remains the ultimate limit for sending information. Before Einstein, we thought of space and time as separate, absolute stages like a cosmic theater where events simply happened. But Einstein flipped the script. Space and time aren't independent. They're woven together into space-time, a flexible, dynamic fabric. Mass and energy warp this fabric, curving it. This is what we call gravity. And here's a beautiful idea. The speed of light isn't just a speed limit. It's the conversion factor between space and time. Move through space faster, and your journey through time adjusts. Space-time is alive, and we're all surfing on its curves. Relativity might seem strange at first, time slowing down, length shrinking, nothing going faster than light, but it's all incredibly logical. Every weird effect is just a natural consequence of a simple rule. The speed of light is constant. Because of that one cosmic rule, the universe maintains structure, order, and causality. It's elegant, it's surprising, and it reminds us that the cosmos isn't chaotic. It's a masterpiece of logical beauty waiting to be explored. Why is the speed of light exactly what it is? Honestly, we don't know. It's one of those fundamental numbers that shapes everything. Chemistry, stars, even life itself. Change it, and the universe as we know it wouldn't exist. Is it a cosmic accident, a design, or just one possibility in a vast multiverse of universes? Feynman would grin and say, "That's the fun part. We get to figure it out." The constants of nature are like the universe's secret recipe, simple numbers, yet they orchestrate a reality more beautiful than any equation on a chalkboard. So, what have we learned? The speed of light isn't just a number, it weaves together space, time, and causality. It sets the stage for the universe's story, where cause always comes before effect. Yes, the rules of physics are strange. Time can bend, clocks can slow, and nothing with mass can reach light speed. But here's the beautiful part. It's all understandable through experiments, logic, and curiosity. Feynman would remind us, the universe is far stranger than our everyday intuition, but with the right questions and a playful mind, it is knowable. And that's the adventure.